Welcome to the next lecture. In previous lecture, we derived the waveform in the waveguide, the rectangular waveguide. What will be the waveform? Today we will do something called TE modes in rectangular waveguide. So actually, if you recall that I have already told you that we call electromagnetic wave to be transverse electric wave if the component of electric field along the direction of propagation is zero. Right now, if you see the figure, my direction of propagation is z, so it is characterized by Ez is equal to 0, and we call it TE wave. Okay, and we will see very soon that the way we have derived the wave equation in previous lecture, there will be two integers m and n, which will determine different types of electromagnetic waves which are possible to be propagated in the waveguide. So hence we characterize it by something called TEMN modes. Okay, it will soon become clear. And for example, if those integers is, suppose m is equal to 0 and n is equal to 1, so that will be called TE01 mode. That will have a different wavelength, that will have a different frequency, different waveform. Similarly, if you have m is equal to 1, n is equal to 1, so that will be called TE11 mode. What that mode is, we will see it very soon. Now, since Ez is 0, but wave has to propagate and energy has to transmit in the guide along the direction z, so hence Hz must exist. That is, the magnetic field component must be then in the z direction. Okay, that is very important. Hz must be there, must exist. Okay, now since Hz is in the direction of z, what will be the wave equation for Hz? We have already derived that using Maxwell equations. Wave equation for Hz will be the Laplacian of Hz is equal to gamma square Hz. Okay, and its solution we also have seen, it will be sinusoidal, and one part will be exponential depending upon the value of omega, value of mu, value of epsilon. And if you recall from the previous lecture, we have written the solution in this way: Hz or before Hz I will write again. If you recall, we solved a general Laplacian equation for any component del to psi is equal to gamma square psi. Psi can be anything. So if you recall, this psi was derived to be in this form: a sine kxx. You go back to the previous lecture, and in that, if you recall, we have case third of the solution, wherein omega square mu epsilon was less than kc square, and hence the gamma g, the attenuation factor, that is real, not imaginary, and that was given up to be plus minus omega under root of mu epsilon under root of fc by f square minus 1, where fc is the cutoff frequency. We have discussed that. Kindly go back to that lecture. If you see, we have written for this case. Okay, so we'll consider that case right now, that if your condition of omega square is like this, okay, then how can we write the Hz component? Now see, this kx and ky will be an integer multiple of pi and a. Okay, that comes from the boundary condition. Okay, if you see this wave equation, what should be the value of this wave equation at x is equal to a, at y is equal to b? Okay, now I will again go back to this figure. Our waveguide is this. Now it has a dimension a cross b. B is the height and a is the width of this waveguide. Okay, so at x is equal to 0 and x is equal to a, that is the extreme points, and x is equal to b, these terms should be 0. Suppose if you take the sine kx term, so then this should be 0. It means kx times x should be equal to m pi. Hence, at x equal to a. So kx times a should be equal to m pi. So kx should be equal to m pi by a. Similarly, at other boundary condition b, we have ky times b is equal to some n pi. So this ky will be n pi by b. So that is why we can write these kx and ky, the wave constants, in terms of multiples of pi and in terms of the dimensions of the waveguide. And this integer m and n are integer, so m can be 0, 1, so on so forth, n can be 0, 1, so on so forth. They will determine the different modes. So hence I can write my equation of hz as some constant, let me write as am, times the sine, and now instead of kx I will write m pi x by a plus bm cos m pi x by a times cn sine, instead of ky, n pi by a times b times y plus dn cos n pi y by b e to the power minus j beta gz. We are considering the third case where the attenuation is there in the direction of propagation. Okay, so this is the wave equation. Now this is wave equation for one component, right? The magnetic field component in the direction of propagation. There will be other components also. So especially see Ez is 0. Ez is 0, then only it is called TE wave. And since it depends upon the m and n, what will be the different frequencies and wavelengths which are permissible to be transmitted, so I will call it TEMN. So Ez is 0, but at Hz we have this form, but there will be Ex, there has to be Ey, there has to be Hx, there has to be Hy. We need to find other components. So how can we find other components? So we have some other equations called Maxwell's curl equations is del cross E is minus j omega nu h, and del cross h is j omega mu electric field. Okay, now we will write its components in rectangular coordinates. What are different components? So first we will write the matrix formulation of this cross product. Here are the two matrix equations, set of linear equations, because I have expanded the cross product. Now we will compare the component wise. Ux component is in x direction, and compare left hand side and right hand side. We will get the following pair of differential equations for different components in the rectangular coordinate system. Let's first write for electric field. So this will be the three set of differential equations for electric field components. Now similarly for magnetic field components, the second matrix. So this is the pair of 6 equations which will give us different components. Now we can simplify it. Let's see. The first simplification is that we know it is TE wave, electromagnetic wave. So Ez will be 0. So wherever we have Ez, we will put that equal to 0. So that will simplify a lot of equations. And the other thing is, if you see the form of Hz, in Hz we have the first form. Let me go back to the previous page. Look at this Hz. Here is the waveform in z direction. You have the x component has sinusoidal terms, the y component has sinusoidal terms, z has this term e to the power minus j beta z. So keep this in mind. Now this Hz, you can see that it is proportional to e to the power minus j beta gz. Now whenever you will differentiate this Hz with respect to z, what will you get? You will get minus j beta g e to the power minus j beta gz, which is actually it will be proportional to, actually it will be minus j beta g times hz, right? So you can see that any differential with respect to z can be replaced by minus j beta g, right? because whenever you are differentiating with respect to z, you are differentiating the exponential term. When you differentiate complex exponential term, the only thing which happens with differentiation is this j beta g comes down and rest remains the same hz. So wherever we have del over del z, we will replace that with j minus j beta z. When we do that, we will get very simple equations, as I will write here. The first one is like beta g ey is minus omega mu hx. Similarly, beta g ex is omega mu hy, and similarly the differential equation will simplify. Okay, so these will be the equations after putting ez is equal to 0, and we will have one more couple of more equations. Minus j beta g hx minus this term, and the final equation will be same except ez is, and here is this equation. Now it is very simple to solve, so I will give some clear hint here. These are a set of linear equations, nothing else. So you can basically, suppose you can represent ey in terms of hy and substitute that ex in terms of hy, and then you can substitute that hy in this equation, any one of them, suppose here, okay, this equation. So what you will do is you will substitute hy is equal to beta g divided by omega mu ex here. Then you get here hz is known to you, and then you will get equation in terms of ex. You have to differentiate hz is given to you, differentiate that with respect to y, you will get ex. You will get ex, then from this equation you will get hy. You get ex and hy, so you can use then ex and hy, which equation? Yes, here hy is given to you, you will get hx from this equation. Hx is given to you, and ey is given to you, you will get hx ey is given to you, you will get this one, this hx, you will get ey here, and then you will get ex from this equation. Okay, so you can just substitute it. You at most you have to differentiate several times this hz. Okay, with hz you have to differentiate with respect to x, with respect to y, you will get, and then I will simply write the 6 components here. So one is ex, that will be equal to, okay, this will be ex. I have written it in terms of hz because hz is known. Similarly, ey will be equal to, right, so ez is 0 because it is te mod equation, and then hx, and hz is derived already, that is this equation which we have, or let me write it again, hz here, hz, this is the hz which we have already derived. Okay, now so we have now what you have to do, see, differentiate hz with respect to x, you will get del hz upon del x, put it here, you get hx. Differentiate with respect to y, you will get hy. Differentiate with respect to again x and y, and put it here, you get ex ey. Ez is 0, hz is given. So we have found all the 6 components of electric field in this waveguide. And what is this Kc? You might be thinking, we have done it last time also. So if you see, this Kc was defined as Kc square is omega square mu epsilon minus beta g square. So we have, wherever omega square epsilon minus beta g square was there, we replaced that with Kc. Okay. Now in this part I will end here. Now in next part I will do the analysis. I will use the boundary condition, further boundary conditions, and will further simplify the waveform equations, and also define cutoff frequency, cutoff wavelength, and then we will also see different modes depending upon the values of m and n, and what is the effect of dimensions a and b on the different modes in rectangular waveguide. We will do one simple numerical also, and then consequently the tm modes, that is transverse magnetic mode, that will be similar. So I will not do that analysis. It is almost same, except you have to put hz is equal to 0. Rest is completely same. And Similarly, the analysis for the circular waveguide, since time was less and because of some issues we couldn't do the various lectures. Circular waveguides, I will not show you the full detailed analysis because derivation is almost similar. We will just do some consequential results, and then we will try to complete other important topics in this lecture. So next lecture we will solve the boundary conditions and get even the further simplified solution. Thank you.